Good day, everyone, and welcome back to my channel where I share snippets from my academic journey. I am Kirby Manalo, and today I'll be presenting a new way to understand volcanic risk, not just in terms of eruptions, but how their impacts cascade through critical systems over time. So this is based on a 2024 study by Ware and colleagues applying dynamic and multi-phase impact models to Taranaki, Monga, Aotearoa, New Zealand. For starters, traditional volcanic risk models are often too static. They focus on one-off hazard events, but real eruptions are complex, involving multiple hazards or multiple phases then, which you can classify or identify as ashfalls, pyroclastic flows, and then we have lahars. Then more importantly, they not only uh, damage infrastructure. They also they also disrupt systems. So thus this paper argues that we need dynamic system-aware tools to truly assess the evolving nature of volcanic risk. As for the research objectives, this study has three main goals. The first goal is to build a framework that tracks volcanic impacts over multiple phases of hazard types. Another one is to account for both direct damages like broken pipes and infrastructure damages. Then we have indirect impacts like water outages due to power loss. Then the last objectives or last goal of this paper is to test this model into Taranaki region, which combines active volcanism with vital national infrastructure. Now let us focus or bring focus to the framework that we are talking about and the first objective. So now let us focus on the framework that we have mentioned in the first objective. This diagram summarizes the structured around which is structured around the eruption phases, which is labeled E1, E3, and E5. And between these, so these are the eruption phases. They are the hazard footprints. Then we have the intervention points labeled as I2, I4, and I6, which represents opportunity to take actions. So this framework contains five modules. One is the volcanic event itself, then the risk management intervention, three is the assets, four is the direct impact, and five is the indirect impact. So what's powerful here is that the damage and the decisions carry forward. For example, if you don't act in I2, then the damage on the E3 will be worse. This gives us a way to model evolving risk over time rather than assuming that the same scenario will happen from start to finish. So this framework didn't made itself or in isolation. The framework was co-designed with the emergency managers of Taranaki region. Through monthly meetings and embedded fieldworks, scientists ensured that model wasn't just theoretically sound, but also usable in the real disaster planning. Let us now elaborate what are these direct and indirect impacts. So direct impacts are those that result from physical contact with volcanic hazards. For example, ashfall impacts depends on the thickness and how much builds up over time. Using fragility functions, these categorize them the damage from IS0 to IS3, which no damage to complete loss, respectively. The HARS, which are fast-moving mud flows, are modeled more severely in most cases. Any contact causes total damage, so it's considered IS3 or complete loss, especially for infrastructures like pipeline, roads, and bridges. Now here's where the system parts comes in. So indirect impacts have happened when damaged assets disrupt services elsewhere. For instance, if a power line fails, it might shut down water pumps or communication towers. The model uses network graphs to simulate these interdependencies. It highlights how a single failure can ripple across sections and how infrastructure isn't isolated. It's part of a web. Moving on to the case study context, let us look first on the next slide, which gives us the figure number 2, a comprehensive spatial overview of Taranaki region. A is map A, or 2A is the map where New Zealand sits along Pacific Ring of Fire, which explains the volcanic risk. Map B shows the Taranaki region, which Taranaki Monga is in the center, a stratovolcano with 33 to 42% chance of eruption in the next 50 years, which is stated here in the uh, information. Number or letter C. This map C shows roads, pipelines, and towns, revealing how much infrastructure surrounds the volcano. Map B explains the geology of the volcanic complex, showing the types of terrains and past deposits. Then E maps the land use from urban zones to farmlands and protected parts. Together, these maps highlight why this region is preferred for systematic modeling. It is geologically active, infrastructure rich, and socioeconomically important, which is why it's critical. Now, you have seen this before. Here are the asset exposure. So this research assessed 6 key infrastructure sectors. First one is the electrical or electricity. Number 2 is water. 3 are 3 is watersheds. 4 are roads. 5 are telecoms. And then 6 are oil and gas. So they source data from both open database and local stakeholders, allowing them to model realistic infrastructure configurations and vulnerabilities across the region. Now move on to the eruption scenarios. So they designed 9 scenarios from small to large, each made up of 6 phases alternating between short, intense events and long sustained activities. First, we have a small one, S1, S2, S3, medium M1, M2, M3, and then the large L1, L2, and L3. When each scenario helps the test how damage accumulates, whether early interventions could reduce system-wide failure later on. Now, for us to deeply understand this table, let us now explain these electricity impacts. So figure number 3 visualizes electricity infrastructure damage at the final phase of each scenario. You'll see in the M2, M3, M4 are L1 and L2. This shows severely damaged largely because of the early or repeated lahar exposure. So the red and orange zones highlights substations and lines that fail completely. These are the red station. They fail completely after the eruption. So these figures emphasizes which scenarios pose great risk and of power systems, helping guides to mitigation properties. Now we are done with the electricity. Figure number 4 shows the final phase damage to water system and southern Taranaki stand out. Southern Taranaki stand out. Now, figure number 4 shows the final phase damage of water systems. As we can see, southern Taranaki stands out here, which is here. And in nearly all medium and large scenarios, acids reach maximum damage or IS3 because water systems often depends on the elevation and surface exposure. They are highly vulnerable to ash buildups and lahars. These highlights that were investments in resilience, like a protective house or redundancy, is most needed. Then, lastly, for the scenarios, let's have the scenario M2 over time. So, here's the figure number 5 showing the time series of damage of series M2. So, for the early phase 1D, ashfall causes moderate manageable damage. Then, but after the lahar events, it pushed the electricity system into cascading failure. So especially when early damage wasn't addressed. This figure is crucial for demonstrating how early smaller disruptions compound over time. And it shows why intervention timing matters and just as much as the hazard intensity. To recap, this study is first in several ways. First one is it models multi-phase volcano event or volcanic events, not just one-off. Then the second one, it integrates indirect impacts and interdependency, making it realistic. Then the third one is it allows the scenario test. It allows for scenario testing, empowering decision makers and plan makers. So to conclude, the Taranaki framework shows that volcanic risk isn't just about lava or ash. It's about how systems respond over time. So by combining science with stakeholder inputs, the model delivers something both credible and practical. It is a scalable tool that could help protect lives, infrastructure, economies, and volcanic regions worldwide. So that is all for our presentation. Thank you so much. And let's see you on the next video.